Okay, hello and welcome. Here we are in lecture 12. So we're going to do a few things today. As you can see from the title, we're going to conclude our fun excursion into functional programming. And then we're going to cover a few other things. We're going to talk about pattern matching, which is a really neat feature in the Scala language. It'll help us do some really cool things in our generators. And then we'll conclude talking about the project for this course, which is still a little bit out of the way. We just want to get some early warning for what's going to happen. Okay, so let's get to it, right? We're going to talk about final few concepts of functional programming we're covering in this course, in particular, flat map, filter, etc., pattern matching, and then some other small details. Okay, let's fire up a notebook. Good to go. Okay, so you've seen us do map in prior lectures. However, usually we're doing map on collections that had single elements, right? No collections where each element, itself is an element. They weren't themselves collections. Now, if you were to work on a collection of collections, map works just fine. It's just now the input to your map function is now a collection, and you're producing a collection, right? So let's kind of see how that looks, right? So for example, let's say we have, a collection L, which is just, a range. And let's say we, for example, maybe map that into with a seek.fill, right? So each element of the original collection is now being turned into a new collection using seek.fill, which is going to, of course, repeat, the element I times of element I. In this case, it's the same for both. So you see, 0, 0 times, 1, 1 times, 2, 2 times, 3, 3 times, and 4, 4 times. Okay, so that was kind of, me making a toy example just to kind of put things together, but let's just kind of appreciate what happened, right? We had a collection, we applied this function, right? And the result of each of those functions was itself another collection. So now we have a collection of collections, right? Now, I could just as well do the exact same thing, but then call flatten on it, which instead of giving me a collection of collections, appends the collections together, right? So if you have like a 2D kind of, a nesting of collections, now it's just all the elements combined, right? And depending on the application, this may be what you want. Maybe it's not what you want, but let's say that's what you wanted. Cool, you call map and then flatten. Turns out things like this happen enough where many functional programming languages have flat map, where with flat map, we can do the exact same thing. The difference is it slightly tweaks the semantics of map, right? So map normally is apply this function to each element, and whatever your output type of your function, that's the element type of your output collection. With flat map, rather than apply to each element, it's going to apply to each element, but it's going to append the resulting collection to the collection, right? And so, yeah, we get the same behavior here. You can do some cool things with this, right? So sometimes you do things where as saw in the trivial example here, where we're creating collections. We don't want a collection of collections. We want just one level of collections and just all data combined. FlatMap will help you with that. But the case I find is most common when programming is actually you have a map function where, depending on the conditions of the element you're processing, you want to return a variable number of things, right? Maybe you want to return exactly what element normally from map. Fine, map works great. Maybe sometimes you only want to return something if something happens, certain criteria is not met, you're not going to return anything. You're going to return 0 elements. Other times you're going to return 2 or 3 elements. So to have that flexibility, flat map is great. And to kind of show that off, here's an example where what we're going to do is we're going to say, hey, we're going to do flat map. And if the element is even, sure, let's just pass it through. If it's not even, we're going to pass empty collection. So as a result, this is kind of acting like a filter. There is a filter operation. We're going to cover that in a minute, but this is just kind of giving you a sense for the sort of things you can do with flat map. It's a pretty powerful, capable thing. I also want to highlight when you're working with flat map, you often have to wrap your resulting thing as a collection, right? If I was to make this seek of I, it would probably complain. Yes, it does, right? Because it needs to be a collection, right? So the result of a flat map function needs to be a collection itself. So that way I can append it rather than just being a single element. Cool. Questions on flat map? Yes. That's a great question. So to give more semantics on the dot flatten operation used above, how exactly does that work? So we start with the um, original map. We saw we have this like 2D collection where it's vector and list, but you can think of both of those as being seeks, right? So basically it's a seek of seeks. Uh, flatten just removes the inner layer of collections and it combines them all. So all of these inner collections are now going to be appended to each other. So yes, it's going to go left to right. Rather than thinking of directions, I might think of it as more, ascending by index. But yes, it's going to combine them all. Now, in the case of a seek, right, seek has an order to it. There are some collections we don't use in this course that have no implied order, like a set or something. Um, in which case, you'd be right to ask, what is the semantics of combining? But in those cases, since the original collection didn't have an ordering, the combined collection will also probably not have an ordering, right? And that also makes sense. But yeah, in the case of the seek, which is ordered, yes, it's going to preserve the order, it just kind of evaporates these wrapping containers around them. Is there a flatten right or flatten left? I think they'd be the same, right? Because uh, we're just kind of evaporating things. So the order doesn't matter as much as you might think. We're just evaporating the collection. So it's still the same content. It's just rather than having the structure of these things being grouped internally, we're removing that layer of structure. So it's just taking all the raw elements in there. Occasionally, when you write complicated functional programming stuff, you'll find yourself working on something and you end up with a collection of collections. It's not a common scenario. Like I said, if you change those commands to a flat map, you can get the one level result, perhaps what you wanted, or you can call it out flatten. But we'll see flat map show a lot of places, so it's actually a pretty helpful thing to be available in your repertoire. Cool. Okay, so make this kind of more visual. So imagine you're running a map. In this example, I decided to have each of the elements in the original collection be collections. That's not required for flat map. Each of the original elements could be a single element. That's fine. But if you apply map, right, you take each input element. In this case, happens to be a collection. You apply the function, and you get an output element, which in this case also happens to be a collection, right? And so um, you can see as a result, we have a collection of collections, right? These innermost things are actually elements, and then there's two layers of collections boxing it in. With flat map, that middle layer is gone, right? It's just appending the elements together. Sometimes you end up with this kind of situation. You care about the kind of result, and like I said, this comes up a lot when perhaps you are going to return a variable or things with your map function, right? Maybe you're going to filter some things out. Maybe you're going to create new elements. Maybe you're going to take some elements out. As an example, I've used this a lot within our code generator. You imagine for everything you want to generate code for, you can generate 0 to 5 lines of code, and that kind of depends on the semantics. And so yeah, our inner loop of our code generator actually has functional programming kind of stuff, flat map, and it's just basically taking these things and pulling them out. Cool. Now, if we go on to the filter concept, to do that, we're going to need something called a predicate. So a predicate is basically just a function that's given a single argument, gives you a Boolean, right? True or false. And so you can imagine, yeah, you can do filter. You're given a predicate function. It goes over a collection. Everything that the predicate says is true, it keeps. But there's actually some other ones that are kind of fun too. So let's play around with a little bit. So starting off, let's make a predicate. In this case, is even. So we're going to be extra verbose and say, okay, it takes in the arguments an int, returns a Boolean, and we check to see if it's even. Okay, so we can go ahead and apply this, and we see with filter, of course, we get all the elements that are satisfy this is even predicate. Perhaps if we wanted to get more spiffy, we could even, generate our function, in line. Same thing, right? In this case, we're able to use that placeholder syntax because there's only one argument application, just fine. This way, to be honest, I think it's kind of very nice. It's very readable. We're being very clear about what is this function doing. Is it even, right? And of course, Scala being Scala, there's both a filter. If you want to do the other option, right, not the predicate, you can do it this way. But to do it in a Scala style, you could do it filter not. It's actually, it'll do the negation for you. So filter and filter not, no reason to even bother doing this negation like that. Now, what's also fun, this I've not seen too many other languages, it has these, existential kind of qualifiers here. We can start, hey, um, is this predicate always true or is it ever true, right? So for all tells you if every single element is even, right? And of course, that's going to be false, right? Because there are some odd elements in there. Now, let's say, for example, I took the results of the even and, plug that in there. Then yes, all the even numbers are even, right? So that's going to check out. There's also an exists qualifier, which returns true if the predicate is true for at least one element, right? So uh, that's pretty neat. So you kind of think of these last two things, the for all and exists, almost as like you applied the predicate to every element, like a map, and then you're reducing it, right? And so for all is like an and reduction, right? They have to all be true for it to be true. The exists is like an or reduction. Um, and so if at least one of them is true, it's going to be true. And so yeah, it's kind of cool to see, is there a case anywhere in this collection if something, satisfies this predicate, exists for all, you can guarantee they all satisfy this. Um, so it's helpful. And of course, filter is super, super helpful. Great. Other questions? Exists and for all. Yeah, these are kind of cool operators to play around with. So yeah, we're going to put them to work. Well, actually, first I'm going to visualize it, but I'll put them to work in a second as an example, right? So filter, of course, we apply the filter function. If it says false, we drop the element. If it's true, we pass it through. But then to apply all that we just covered, I'm going to generate primes. And we're going to do kind of a fun pass. So the way we're going to do this with a prime sieve. So sieve is an algorithm that, does passes over numbers. In this case, a prime sieve finds, primes. So we're going to build it up programmatically using functional programming. To me, it's actually a pretty, fun, elegant use of some of these techniques, right? So let's first define a function multiple of, which given two integers will return if, A evenly divides B. Now, what's interesting is because we broke up the arguments with curring, we covered this last time, we can now put two and two together, right? So in other words, given a collection of numbers and a number x, we can now remove all of the elements that are multiples of that number, right? So how are we doing that? Well, we have this predicate which, if we give it the first argument, it's going to get locked in there. So in other words, multiple of, in this case, x is going to be a function that returns true if the number evenly is divided by x and false otherwise. Okay, so in other words, that's going to be true if something is divisible by x. Now by doing filter not instead of filter, we are going to keep all the things that are, or so remove all the things that are multiples, right? So maybe it's good to kind of temporarily comment some stuff out and we'll kind of show what's happening, right? So we show all nums. Yeah, we know all nums is a long list of things. If we, filter all the things that are not multiples of 5, right? Now, let's say, for example, I forgot to put not on there and I just did filter multiples of 5. Well, then those are the things that are multiples of 5. We want to drop those, right? So that's that example. Alternatively, we could use this function we just defined, which does filter not for us. So yeah, in that original pool of 100 numbers, we've now dropped all multiples of 5. Cool. So now to sieve is interesting how it works. To sieve, forgive my Greek, Erasmus, if I'm pronouncing that horribly bad. What you do is you take the numbers you're curious to find if there's any primes there, and you just go through it in ascending order. And for every number, you remove all multiples of that number remaining. And so as you go up and you reach a certain number, let's say a certain number x, if it's still in the collection, that means no number smaller than it could evenly divide it. Thus, the number is prime. And because you decide that number is a prime, you're going to remove all multiples of it going forward, right? And so we see how this kind of works. We take the collection and we're going to return a collection. It's going to be the original range, and this is going to be the collection of primes. So the base case, okay, if we get an empty collection, we're done. But the common case is we're going to take the first element, we're going to declare that prime. And then we're going to remove all multiples of that thing in the remainder of that collection. Now, I'll spend a quick second to point out there's these notions of head and tail in Scala. So head is a single element. Tail is every element of the collection other than the first element. So these are only available in the ordered collection. Seek is ordered, so we can do that. So basically saying, okay, remove the first element, and then work on those elements. And then, oh yeah, by the way, we're going to remove all multiples of the first element. So yeah, this actually is going to work. Maybe it's better if I print out the results. You can see, yeah, these numbers might look familiar because those are, the first few primes under 100. So in just a handful of lines of functional programming, really, this is just comments, right? We can do it like this. Of course, you didn't have to define this function. I felt it was just helpful to kind of have that, more explicit, more deliberate description of it. For fun, we could try to do it without defining the function. See if I can do that. Filter not. We are going to get an arbitrary number and then see if it's divisible by x, right? That should be the same thing, yeah. But cool. So this is kind of, using that FP stuff for some stuff. Hopefully see some grace and elegance here, some conciseness here. It's also, strong rigor potential here, not necessarily the way I've written the code, but theoretically possible here with the functional program to kind of have, strong confidence in putting together, robust components in a robust way. Question, yeah. Correct. Yeah. Yeah. Good point. Maybe I can even demo that real fast, right? So I can say print line all nums dot head and all nums dot tail. So you can see, yeah, head is the first element and then tail is everything else. There is also a dot last in Scala, and there's a name for, so like head and tail create the full collection. I forget the one that goes with last. Someone might know. Is it first? I was like, oh, I can't. Am I crazy? No, not first. Um, Maybe tab complete can bail me out. Ooh, yeah, this is promising. Okay. Let's see if we find what to us looks like should be in it? Maybe. Oh, you found it already? Okay. Yes, so it's possible to break it up multiple times. Yeah, you can see first element, everything else but the first, everything but the last, last. So those are both available. So like I said, once again, Scala has a lot of rich features in it. Not every language has these. You don't think to look for them. I have a slide even today talking about how it's kind of cool to find these things and try them out. And yeah, I mean, when they're there to kind of decode more concise, you can have a longer PL discussion about, is it good to have a lot of features and have, more concise code or fewer features and more verbose code? It's almost like a risk versus sith debate rebranded. Um, let's see. Is there a dot? Maybe not. Or maybe it's another thing I don't know the name to search for. What is dot end? Dot end didn't do anything. Oh, it's beyond the last element. Oh, interesting. So it's only available on a range. It's not available in the seek. Cool. But yeah, independent of that, right? Look at this. We built a prime sieve in just a couple of lines. It's pretty cool. I wouldn't say this is hyper algorithmically efficient, but also not hyper algorithmically inefficient at the same time, right? Because as the sieve operates, right, this collection gets smaller and smaller and smaller, right? So there is some, benefit. The numbers that get passed the most times in this collection, of course, are the primes. Because you can imagine after doing two, right, you've already cut your collection in half, right? What's remaining? Because you've already deleted all the even numbers. And after three, you deleted half of what's remaining because, half the multiples of three are even, those are already removed. The other half the multiples of three are not even, and those ones are remaining, and they've also been blown away. So you can see how, actually now I'm just really curious. Let's have fun. Let's print s.size over time. And we can watch that. Oops, I didn't need to put that there. Don't need those. You can see it just like shrinking pretty fast, right? Cool. So independent of primes, the whole point is to show, hey, we're doing filter, not filter. In this case, also doing recursion and blending recursion with our filtering function, right? So very functional. Cool. Other questions? Cool. Okay, let's keep going. Um, I said Scala's got a lot of stuff built in, right? So we saw some of these last time, right? If you're doing a reduction with an add, there's a dot sum. If you're doing a reduction with a product operator, there's a dot product. If you're doing a reduction with min, there's a dot min. If you're doing a reduction with max, there's a dot max. So for all these common cases, you can just get by using these built-in things, right? So that's pretty cool. That's handy. Things like dot sum, that's really pretty spiffy. Cool. So as I kind of shown these prior few examples, there's a lot of these kind of conveniences built into the language. Like I said, it's a rich set of these API methods. You've seen a whole bunch, right? Is empty, not empty, right? A lot of languages bother just is empty and count on you negating it. No, there's also non-empty. We saw to versus until. Whether it's inclusive or exclusive in your range bounds, we saw filter, filter not today, fold left, fold right previously. And so of course the challenge is if you're learning a language, you may not know these features or idioms exist, right? And you can write perfectly correct code that perhaps does one method and then negates it or does the according thing to get the result you want. And so this is independent of Scala. It's always just, well, how do people to kind of learn about these features and adopt them, right? I'm going to give 3 solutions, and I want hopefully you'll do all 3, right? Number 1, I keep pushing IDEs for this course. I swear IDEs really help writing Scala and Chisel. So some of these things you do one way. The actual IDE will give you a suggestion. You know what? You can do it this other way, and the other way is tidier, and that's nice. Step 2 is actually looking at other people's code, right? Whether it be as part of a code review or even just looking at code online, perhaps you'll learn certain tricks, right? And we'll be doing code reviews in a bit in this course. And then step 3 is actually a blog that was written a few years ago, but I've been recommending every quarter in this course. It's been linked from your course website all quarter, but I'll just pull it up right now. It's actually pretty lengthy, but it's good stuff. So in here, this developer, Pavel Baden, shows you a lot of things about Scala, maybe slightly different in their languages. And he shows, you can do things like, okay, instead of having to do sorting, the long way, you can just say dot sorted. That's in Scala, right? So there's a lot of examples he brings up of ways people might do things, and you actually learn the full Scala, to embrace things, and it's there. Cool. So yes, please take a look at this blog. Use an IDE. Try these features out, right? Like I said, this course is the grad course, it's an elective course. So why not have fun, right? Why not try out new programming things, try out functional programming, try out some of these cool language features in Scala, see what you like. It's kind of fun. Yes. Yes. Yeah, so the comment was about using the IntelliJ IDE and some of the things it gives feedback on. So yes, it will give you feedback on things that are not compile errors, but are things it recommends for style. I am 80% confident, but not 100% confident that it uses Scala style as the underlying engine to do that kind of stuff. So Scala style is a independent, package that's available on the web. IntelliJ is just nice that it bundles it and doesn't even ask you to set it up. It just does it automatically. But if you were so inclined for Scala style, you can actually make your own style Scala. So you can give your own def file, and you can say certain things Scala style checks for. You can say, you know what? I disagree with that. This is my style. I want you to check for it this way, not that way. And you can tell it that. So that's definitely something you can check and look into. Cool. Okay. So then let's rehash a homework problem as well as scale up, right? So let's say we want to do matrix multiplication but we want to do it using functional programming. Cool. Okay. Um, so how might we go about doing that? Well, just for today, we're going to have this made up, matrix. Sure, we'll just, I'll run this first so you folks can see what this is. It's going to just, we know seek.tabulate. We're just going to make an arbitrary matrix, 2D set of lists. Cool, we got a matrix. Now I find for doing matrix multiplication, there's many ways to structure this code. It's very convenient to be able to grab a column, right? And the way this layout is set up is kind of row major, right? So to grab a column, how might we do that? Well, let's say given a matrix, which is, a 2D seek. There's a type signature, right? This is a seek. Seeks are generic types. What's the type of the seek elements? Also seeks, but in this case, seeks of ints. So that's a 2D seek. I, in this case, maybe it's more clear to make that, call. This is the column we want, right? So go ahead and run that. Sure, so we would define a function that grabs the column. So if we want, let's say, the first column, which is actually not here, but, so column 1, which is the second column technically, right? It's going to be right there. Cool. So that does that. Here we're applying map, right? We're applying, going over each row and getting a certain element, right? So this map function takes in the collection and returns a certain element, taking advantage of the fact that seeks can be indexed, right? So that's pretty cool, right? So, okay, so now that we have the ability to grab a column, how am I building matrix multiplication with this? Well, one way to think matrix multiplication, of course, is that you're doing the dot products of, the rows of the first argument with the columns of the second argument, right? So let's do a dot product. So given a row and a column, which better be of the same length, we're going to zip together elements. Here I'm trying to use the functional programming features. Then for that collection of elements, we're going to have these pairs, right? Something from the first collection, something from the second collection, because of the zip. Multiply those together, right? Pairwise multiplications. And then reduce the whole thing. So we could have, done dot reduce. Hey, dot sum exists, right? So let's use dot sum. So cool. We now have the ability to do a dot product and actually put all of this together to actually do a matrix multiplication. We now need to set up the actual matmul, right? In this case, because I'm lazy, we're doing the same matrix as both the first and second argument, but the function, the codes themselves is nodat. I'm showing this 3 different ways, right? So the first way, why don't we try going row major, right? So for every row in the first matrix, so we have a row of A, it's produced by that first map. We actually want to go through each element of that row, and we want to zip it with the column index. Okay, if we do that, we get the result is going to be the elements with the column index. But the things we really care about is actually the column index more so than the thing. And then we go ahead and go through this, and sure, we can go perform a dot product on the row of A, and then we need a column of B. Well, we can use our grab call thing we just defined. So this is going to work. If I zoom out, you can barely see it, but you can trust, hopefully, that's the correct result, right? And so I see some interesting faces. And so, yeah, this is the thing with functional programming where sometimes it's not super obvious to read someone else's code, right? It's like, what were you thinking? So I'm going to take some questions right now. Yes. Oh, so right here, matmul is not given a return type. Great point. So Scala has type inference, so you are not required to have a return type unless it's a recursive function. Now, required is the key word. Style-wise, we'll find it often very helpful to include return types for clarity. The IntelliJ IDE on a public function will give you a yellow squiggle underline if you don't give it a return type. Not typically required. But yeah, we could definitely put that on there. No problem at all. Yeah, it's doing type inference for the return type. The recursive functions require you to give it the return type because, of course, circular logic is hard for it to infer it. Cool. Other questions? Perhaps for this inner body, you might argue this is one way of doing it. Another way of doing it, okay, given a row of A, what we actually really want to do is 0 until row of a dot size. Then you say map call index. So this is another way of doing like the same thing. If you don't want to do zip, because you aren't really doing a zip in this case, we're just taking the range. Um, you can see there's always kind of different ways to re-express things. Oops, and I lost track of a parent somewhere. Um, uh-oh. Oh yes, I need one more for the dot P. Great, okay, so perhaps you find that more clear. Like I said, everyone has their own style. To be honest, in hindsight, I actually argue this one is better because, yeah, the element here is a distraction. Um, Maybe a more for loop S style way of doing it, even though it's technically not for loops, is down here. You can see once again, just another way of writing this. Here we're using the ranges. So a dot size is the number of rows. This is the uh, length of one of the. Actually, that should have been a dot head. Yeah. Okay. Never mind. That should be like that. Okay. So given I and j is a row and column, well, we can simply say, hey, give me a row of a multiplied by a column of j, right? Or maybe this one's more intuitive for people. I wouldn't worry so much about line count. It's more about just what do you think is simpler code, easier to kind of to rock with, right? Um, and then this pattern of nested loops with numeric indices. That's what tabulate's for. So we can throw tabulate this, um, and it should be able to do it, right? That's the most concise. So I don't know. Folks have strong opinions, comments on these different ways of doing it. Yes. For which example one? Okay, this one. Okay. Oh, so in this case, the element's actually no longer a collection, right? This is an element as it iterates through the row of A, right? So if we're calling on row of A, zip with index. So for every element of A, so it's almost easier if I actually print this. Um, let's see. Oops, I should do multiple lines and then comment this out. And actually, so we can see the result, I'm going to make sure I don't lose my buffer. And then I'll say, okay, print line. Oops, I can't do a print there. This is getting more complicated, but I can do it. Anything's possible. Okay, so we can squeeze in a print line. So we can see, it's going row by row through this. And so this zip with index right here is going to pair it up with all the indices, right? So now you see 0, 1, 2, 3, 0, 1, 2, 3, and the elements are changing, but it's the indices paired with it. So then we're applying a map onto that. So then using pattern matching, this case statement, we'll explain that in more detail later today. It's now taking this pair of things, and the thing on the left in that tuple is being associated with element, and the thing on the right is being associated with column index. And as we discussed, we actually weren't really using elements. So perhaps zip with index wasn't the ideal use in this case. Perhaps it's better to do it like that. No, no, row of A is literally a row of A, right? It's a seek. That would be a single element. Yeah. Yeah. So because the original structure is 2D, um, when I grab one of these elements, I only get one row at a time. The problem is we already need grab calls. We want to get a column. which, how do we do that? Well, we have to go across all of the rows and grab a certain index. Yes. Returns an integer. So the dot sum is the reduction, right? So at this point, we have a collection. So we have, let's go through it, right? Collection, now with a zip, collection of pairs. Mapped, now it's also a collection of integers, and then it turns into a single integer. And that's the thing with functional programming, is you can have these really concise expressions where sometimes it's helpful to kind of, see every step of the way what's going on. Yeah, grab column returns a seek, correct. Yeah, so it's a good question. How do I get, so the final result of a mapmul, as discussed, is a 2D seek, a matrix, right? And so what are we doing? Well, we are basically, if you want to think of it as using linear algebra terms, we're producing this in terms of output elements, right? One output element at a time. There's a lot of ways you can do matrix multiplication. The way we're doing it right now is one output element at a time. So for each output element, we're computing it using a dot product, right? Of the appropriate row and the appropriate column. And so to set up that iteration space, right? It's a 2D output, so we have a 2D iteration, right? So yeah, here we have, one iteration with a map, another iteration with the second map right here. Perhaps I'll remove this intervening stuff that was kind of making this whole thing a little bit more complicated. Right, so that was one setup, and then remember we had the other two ones. Oh no, we talked about this. They're gone. Luckily, I've got Git, so they're not gone forever. But they're gone for the short term in this lecture. But the other methods also had the two things nested in there, right? One of them was, using the ranges with two map calls. So two nested map calls was going to produce a 2D result. And the last one was a tabulate, but the tabulate arguments had two parameters, meaning it's going to be like two nested calls. So each of these calls says we create like one element, and we're just creating one element at a time of a result matrix. There's a map here. No, that's what I'm saying. One map, two map. Right? So you get a 2D result because you're doing a map within a map, right? So there's a map up here and a map down there. So yeah, so all these things combined have like nested iterations, right? So it's either map and a map, depending on the other one, or even a tabulate, but tabulate multiple arguments is like nested maps. Yeah, so this is a good style question. The Scala community tends to actually encourage or enjoy having like these like leading calls on a line. So it's like a function body, and you can imagine a function body. Normally, you could do, okay, hey, it's a function, and inside the function, do a map. But then everything's in response to that a map will be moved over one indent. And if that's like the entire body of the function, styles encourage, you know what? Let's remove a layer of braces and do that right there. And so it's semantically the same. It's just a matter of how you're bracing it, right? You could have like, a function set of braces, and inside that function, there's basically one line in quotes. That one line is a multi-line map. Or you can recognize that your entire function body is that multi-line map and just kind of elide that last little layer. So as a result, occasionally there's surprisingly important keywords in the first line, which, you gotta keep an eye out for those. Good point. Great question. So this is really helpful to have this conversation. So this is functional programming via conversation, which is a great way to do it. Yeah, exactly. So remember Scholar, there's no semicolons, right? You don't see me adding semicolons. It's able to kind of parse all this, right? So yeah, it's like, oh yeah, I follow equals until, it ends, right? And so, okay, well, what's the statement? The statement is a map, and then when is the map's, function literal end? It ends here. Okay, so that was it. This is the one line function, which just happened to have, a map, and then this, yes, there's, more characters to define the function literal for that map call, but it's a one line function in quotes, right? It is, right? It's highlighted, it's green. And yeah, I'm sorry I lost the second and third functions by losing my copy paste buffer, but they'll be in Git. I'll get them back. Okay. Um, oops, let's get this reactivated. Okay, so as promised, actually, wait, I'll go back one slide. Any more purely functional programming questions before we shift gears halfway? Yes. Nested maps are very much very similar to nested for loops. Some advanced Scala programmers even really like, remember I showed you very briefly early in the quarter with for? You can have a nested for loop where you only write the for keyword once, and you kind of have your multiple iteration ranges all packed in there. That is also possible. Um, so yeah, so for can act like that. Okay, so now pattern matching, which is a feature that Scala, along with other languages, are introducing. When it first came out, super exciting. A lot of languages have copied it because it's really freaking helpful. So there's a few places where it comes up. We're gonna start off with a match keyword, but it's not the only place you can do pattern matching. But basically, you can think of this as like a much more flexible switch at first, where normally with a switch you'd have like a type that's discrete, like a byte or int, and you kind of go through it. In this case, we can say, you know what? You can match directly in something, sure. You can use ors. So I want to match if it's 1 or 3, but have only one function body at the bottom specifying it. Notice how for all these things, what we're doing is, given a certain case, we aren't just, in that code block, we are now going to return something, right? So this is kind of, still making a function. It's almost like a function lookup table in a way, right? Given a 0, we get this. You can have flexibility, right? 1 or 3 maps to the same thing. Or interestingly, you can write conditionals, right? So I'm going to give it a temporary variable name and then say, hey, is that thing even? Or maybe 5, we think it's a special number. And it's also a default case. So for example, we'll start playing with this. Okay, yeah, if it's 0, it's going to match with 0. If it's 1, it matches with not. That's whatever I chose that day. If it's 2, it's going to be even. If it's 3, it's also going to match with na again. Okay, if it's 4, it's even. 5, look, we found it. 6, of course, is going to be even. And then 7 doesn't match anything else, so it goes to that default case. And so you see this in a few places in the language, where basically when you have something you're trying to line up with things, you can use this case expression, right? So you saw that back here, for example, where we had this tuple coming in from a zip with index. We can match it up a case, right? And then, in this case, we're matching it with numbers. I said you can assign things, you can apply ifs to it. So this is kind of a good starting point. Questions so far? Yes. So can you explain that case more often? Oh, could I do this through state machines? Um, so yes, as a functionality point of view, no, because this is pure Scala, right? So that's why you saw that earlier in the quarter when we introduced finite state machines, we used the switch keyword. Switch is not part of Scala. It's actually part of Chisel, and took advantage of the fact that Scala doesn't have a switch we use a term people recognize. So that's something we show as a way to write state machines for that sense. That way the matching is done in Chisel in hardware. This is in Scala, right? Which, believe it or not, there'll be cases where you actually do want to do pattern matching in Scala on things. You have a really flexible generator, you want to kind of handle multiple scenarios. And you'll see, for example, in a second, with this pattern match capability, you can do things like pattern match on case classes, which is a really helpful way to, for example, to carve up cases based on your parameters, for example. Cool. Okay. So then, now just a minute. Let's do it now. Okay, let's say we want a pattern match on case classes, right? So we have two case classes, helicopter and submarine. They both include a color of the vehicle as well as a string for the driver. Um, so this is enabled by an abstract class, which I didn't cover explicitly, but I think given prior functional programming, object-oriented programming experience you might be familiar with, right? The idea of an abstract class is you can define a class, you can never instantiate it, but by defining it, other classes can extend it to their concrete classes that actually are instantiable. And the reason why you go through the hassle of having this abstract class is that way you can make them the same type, right? Because if I didn't have these two classes inherit from the vehicle abstract class, it would just be two random case classes, right? But now they're both case classes that extend vehicle, so then everywhere vehicle is allowed, they're allowed. So, for example, let's say I had a collection of, movers, which was, a gray helicopter, driven by Marta, a blue helicopter driven by Laura, and a yellow submarine with Paul, right? We can match on these, right? So, for example, let's say, given what we're dealing with, if I have a helicopter, notice how I can match on types of case classes, right? That's pretty handy. This is printing just for fun. But yeah, the key thing is, here we are matching on them, sure. And we can do, not just matching by type, we actually can define these arbitrary patterns, right? I can say, you know what, I want helicopters that are blue, and it's gonna, based on this match, not just find helicopters that are blue that match this condition, it's gonna assign the variable driver to fill in the driver field. So that's pretty cool, right? So now it's gonna say it didn't match because none of these helicopters is blue. Or sorry, Laura's a blue helicopter, right? And that'll tell us that. Likewise, if I have a submarine, I can, assign it this way. I can say, hey, I have something of type submarine S, and I can, match on this color. This is a more verbose way of doing it. Perhaps this way is more concise above. Or I can say if it doesn't match, right? If it doesn't match any other cases. So you can see how pattern matching is extremely flexible and extremely powerful in Scala. Cool. Yes, question. Yeah, so the fact that this driver is the same name as this is not required, right? This could easily be, dry, still works just fine. This is pretty cool. Sometimes I said you'll be given a collection of case classes and you only care about certain fields. Um, you can, in a local scope, give those fields names and work on them, or you can even, check them manually, or if there's a certain value you want, you can just put that right there. So it's a very intuitive syntax, right? I want blue helicopters, right? This gives you blue helicopters. Um, and so yeah, here's pattern matching, meshing well with case classes. So you said very commonly you use case classes for parameters, and so this is a way to have a really flexible way to kind of build top of parameters and pass things around. For a simple, trivial one module, this may not be very obvious. You can imagine if you're building a much larger system where you have a lot of generators that in turn calling other generators, you have this complicated collection of parameters, and you want to pass things around. Being able to match on things and to extract fields or check for certain traits is really helpful. But yes, as you can tell from Scala so far, the forms of objects are increasing, right? We had class, we had object, then we had case class, now we have abstract class. There's one more coming later on this course. Like I said, there's a lot of features in this language, but they're helpful. Yes. Yeah, our abstract classes are like virtual classes. Yes, exactly. Uh, Basically, they exist so that way you can have a common ancestor, not because you're supposed to instantiate them. You actually can instantiate them. Cool. Oops. Okay, so then remember I taught you about the option type in Scala a few weeks ago? Let's say, for example, let's just generate one for fun, which is going to be a seek. Okay, take all numbers from 0 to 5, but for the odd ones, we'll put in the collection as some number, and the ones that are even, we're going to drop, right? So if we just apply this right, this is a seek of an option type of ins, right? You see some things exist, some things do not exist, etc. And so sure, we can go through and iterate through it and check for the ones that do exist, we can print. Now that we know functional programming, we can do some more graceful, more concise ways to work with these option types. So for example, one alternative is something might be an option and you're able to make progress without it, you can say get or else, right? If it either succeeds in getting it or it is some other number, right? So for example, 1 actually is in the collection, so that works just fine. 0 is not, right? So 0 is going to give you -1. Um, Now, what's more fun, for example, is something like this one, where you can say for each on a single element, right? So what's interesting about for each on a single element, it's only going to do it if it's something there. If it's none, it's going to skip over it. So there is something there, it is going to print it out. Okay. We can, of course, flatten the collection. So basically, it's going to drop all the nones. Cool. We can do the matching we just talked about. So if it's something, we can go ahead and print it if it's something. Otherwise, it's none. So notice how in this case, this is one way to like extract that option using pattern matching, right? So we saw this before, right? So let's say this could be a map or a for each, whatever you have going on. We basically give it an option. We're assigning a temporary name to the actual value inside of the sum. So now we actually have that value we can go play with. Or if it's none, we can, acknowledge it's none. And this is the same as above, so we can delete that. Cool. So here's some more graceful ways to interact with option. And occasionally you're reading someone's code and you see them call like for each on something that you know is not a collection. Like, why would you call for each on something or map on something that's not a... And the reason why they're doing that is because if it's an option type that has the behavior of either performing an operation if it exists or doing nothing if it doesn't exist. Cool. Other questions? Okay. Well then, I wanted to pitch. Ooh, that's a typo. I'm gonna fix that right now before I forget. Sorry, folks. Uh, this is the one pitch the project now. You still have a little bit of time, but I want to put it on people's roadmap, right? So, as you're well aware, we're doing all these lectures, all of these homework assignments to get you ready to do the project. And the project's kind of the real learning happens, right? So far, you're kind of becoming great Chisel, Scala developers, but you actually want to build a whole system, right? Get good at actually developing a new hardware generator and actually go through the whole system. And so, what's that going to look like? Because we have 20 students turning in assignments, although here in person we have about 13, maybe 12, due to simple time reasons, I'm basically almost requiring pairs. If you have a really strong reason why you need an individual, come talk to me, but otherwise, please find a partner. And the idea is for you to make a generator, right? So by now you've seen some of the things you can do in Chisel and Scala. If you're looking for inspiration, you can skim through some of the past projects which I linked on the homepage, or you can talk to me in office hours. I have some, available ideas you might come play with. And the point is, when you actually have this project, you're going to do a whole bunch of things, right? You're first going to propose a project. You're going to get feedback. You're going to go ahead and design your generator. You're going to develop the generator. You're going to test it. You're going to optimize it. You're going to revise it. Here's the whole thing. You're going to document it, and then finally present it. So because of all these things you're going to be doing, and because you're starting larger from scratch, because you're doing a unique project to you and to this quarter, it's going to be, much more work than doing the homework. The homework problems, I try to give a lot of scaffolding in terms of not only some of the surrounding code, but I also, for example, do things like try really hard to specify the problem, right? Versus when it's your own project, you're not the one specifying the problem. Like, how should things go fit together? That's for you to figure out, right? Now, you're not going to be alone. You're going to have a partner as well as this course, right? Please ask questions on Slack. Please come to office hours. This is kind of fun. It's really going to make things happen. I just saw when I first changed the slide. Yes, I did change that constant on the slide. And the reason why is that's part of what's going on in my revisions coming into this quarter. So looking in past quarters, I decided to place a greater emphasis on the project. As you saw earlier in the quarter, I also increased the grade percentage for the project. And we're also doing the homeworks like a touch faster than prior offerings. And the reason why is I want to make more room for the project, right? I want folks to do bigger, more ambitious projects. I think you can do it. So as I said, what's the timeline? We are in week 5. This is a 10-week quarter. So for now, the goal is to find a project partner. For example, if you want to, maybe even use a project Slack channel to find someone. and start thinking of ideas, right? And if you want to come chat office hours to get feedback on ideas early on, that's totally cool. If you want to see if I have any hand-baked ideas, I might have some. Come tell us to me. Um, but eventually, you're going to need to put those ideas down on paper in a proposal, only one page, and then you're going to meet with me during class time. We'll have to put a schedule out when this comes to get feedback, right? And so that way, I'll give you, verbal, conversational feedback about the proposal, about things to watch out for, things that were lacking, that sort of stuff. And then you can start coding, right? And my whole goal is to have you folks close the loop as early as possible, right? I keep saying this all quarter, right? Close the loop, right? So rather than doing a bunch of coding and then seeing to how you integrate and how you actually run it, no. Get something running as soon as you possibly can, even if it's really minimal and feature restricted, and then keep adding on to revising and extending it. You're going to keep developing, and then finally conclude. The end game is going to be presentations in the final week of the quarter, and the week after your opportunity, if you wish to revise your slides and your code, you can. But we're looking to have polished presentations that final week. There's some intermediate deadlines along the way. For example, at one point, we're going to ask you to send, I would say to staff, but staff of one this quarter, a link to your GitHub where for the appropriate commit you tell me, I want to be able to clone and run something. Doesn't need to do everything, but I want to see something working. I want to see some code doing something as an intermediate checkpoint. There's also going to be a code review, which I'll come back to later on, but the code review is going to be a way for you to see people's code and get feedback, but also because someone's going to be reviewing your code, hopefully that should be incentive for you to make your code a little bit better. So cool. Here's the more concrete listing of the timeline, right? As I said, there's going to be a proposal due, and you can see 15 days. So it's not, tomorrow. Don't go running off a bridge. But hey, find a partner, figure out what topics might be interesting to you. And let's say there is a direction that is interesting to you, but you don't quite know what the project is. How do you make a generator that's reasonable size? Look for stuff, right? Look for stuff online. Has it been done before? What sort of things are available? What's the price of the art in this thing? Also helpful for projects. If you're building something, maybe you can find a Python or some other language version of that functionality. So that way you have like a thing to compare against, right? To kind of test and get bootstrapped to see what the right answers are. Do you have example inputs and outputs you can play with? We've had students do things like, auto processing, right? And so for auto processing, yeah, they found a Python version that had, they could use to see what the original input and output should look like to kind of be the way to kind of test their model. As you've seen so far in our course, right, I'm advocating for, building a behavioral model and then developing after that. This is kind of exemplified by this week's homework, for example, with the matrix multiplication, right, where you build the model, then you build MapMul, right? Or last week with the game of life model, then you build game of life, right? So that's kind of model I'm recommending is you build the model and then you build the hardware and make sure that they agree. So finding a good proposal or a good topic, maybe you can find something, even though you write a Scala model, if you find a non-Scala model that helps you get started, it's another way to get going. Like I said, you're going to ask for intermediate checkpoint of having your repo. There'll be an external by another group, but a still classmate peer code review, presentations, and then I said there's an opportunity in the final week to revise things. And so following the presentation, I do send feedback out via email, and then you have a chance to revise your slides to get the remainder of those points, as well as to keep hacking on your repo. And the final grading will be both on the presentation and the repo itself. Cool. Questions? Yes. Oh, good question. So there's going to continue to be lectures in this course. There will be a couple of guest lectures. Speaker lineup still TBD, but yes, where I'm sending out emails. And then we're dedicating at least 4 class sessions to the projects. So 2 of them for feedback, 2 of them for presentations. As always in the course, you want to be prepared to be for anything. If it turns out, we have so many projects, we really need more time. I reserve the right, of course, to have a third day presentations or something to make time for them. But I believe if we have enough pairs and not too many singletons, we can get through presentations in 2 days. But yeah, to give you the ballpark sense, right? These class times are 65 minutes, right? So that means I think it would not be unreasonable to have a really polished, really clear, 10-minute talk or 11-minute talk, and then a couple minutes of questions, and then hand off. We could do 5 of those per class with 20 students, 10 projects. That math kind of checks out. But like I said, if it turns out we really need more time, I can invite one fewer guest speaker, and we can make the time available. The later lectures are more flexible in ordering. So you saw so far, we've kind of had this like really quick cadence of lectures, making sure you have enough chisel to get there. Now we're getting a pretty advanced chisel and Scala, right? So you can, even if I was to stop lecturing today, you all know quite a bit, can get quite a bit done. And so it's not the same level of urgency for me to cover material in lectures. So yeah, depending on availability of guest speakers or the needs for projects, we can adjust the schedule. Cool. Other questions, comments? Okay, well, that's all, folks. Sounds good.